Hello, and thank you for joining us. Today's webinar is Laser Ablation 101, an introduction to the technique of ICP-MS. Our presenter today is Lucas Smith, Director of Business Development for Teledyne CETAC. We will be taking questions, so feel free to submit your questions throughout the presentation using the question feature, and your questions will be addressed at the end of the presentation. Also, this webinar is being recorded and will be available for viewing within a couple of days. You will receive an email notification of its availability. Now I'll turn it over to our presenter, Lucas Smith.
Thank you, Shelley. Good afternoon, everyone. Thank you very much for joining today's webinar, which is intended to provide an introduction to the technique of laser ablation. Now, when we say introduction, please keep in mind that's exactly what we mean, as I'll cover a lot of the technique's fundamentals, and I'll try and present it for the true layman. But please keep in mind that ordinarily, it's not uncommon for me to visit a university or a commercial lab and provide this kind of information over the course of a couple of hours. And today, of course, we're going to try and squeeze that into 30 minutes. So we obviously won't be able to touch on everything, but I think that we'll be able to give a solid foundation, a good place to start and ask questions from. Now, for those of you that are interested in a more in-depth look, either at the history of the technique, recent advances in it, or detailed applications, please know that we're going to continue this as a series for the next 2 weeks, and I know that a lot of you have already registered for those. I'll talk a little bit more about the both of those seminars as we continue through. Okay, so as far as content goes, what are we going to cover today? Well, we're going to start by defining what laser ablation is. And as you can imagine, it probably wouldn't be much of an introduction to the technique if we didn't start there. We will talk about it relative to other analytical techniques and talk about some of the advantages that it provides, exactly why we should be looking into it. We'll also talk about the different laser sources and how to select between them. And we'll talk about some of the more important laser topics, such as washout times and fractionation, before finishing with some application examples and, of course, the Q&A session. Okay. So for starters, what is laser ablation? Well, in its most basic form, the idea of laser ablation is that we're going to take a beam of concentrated light, we're going to blast the surface of a sample, which could be of a variety of things, and when we do that, we're going to ablate it. We're going to remove some amount of material from the surface of that sample. How much depends on a number of factors, including how powerful the light was, the density of the material, how transparent it was, and a number of other factors. But we're going to take some of that material, we're going to ablate it and kind of blow it up into an analytical plume that comes off and swept into the ICP torch. Okay. So this is in direct comparison to the traditional elemental analysis by aqueous, ICP, OES, or MS. The difference essentially being that we get to avoid the entirety of the dissolution step that comes first. So we're able to avoid the digestion with acids. We're able to avoid the requirement for a microwave or a hot block in order to help that digestion process, and it saves a lot of time because of it. We also then are able to realize the second major benefit after avoiding the dissolution step, which is the maintenance or the maintaining of the spatial resolution for the sample. So if you were to take any sample, regardless of what it is, it could be a rock, it could be a microchip or anything else, you think that if you were to take that sample and do this by traditional aqueous analysis, you would start by dissolving it and then put the resulting acid mixture into the ICP-MS. And essentially whatever was in that rock or microchip is now in one homogeneous solution that's going to be analyzed. What laser ablation allows us to do is start with the solid sample. So by avoiding the dissolution step, we're able to tell if one corner of the microchip has the same elemental composition as another corner, or be able to go through layers of it and analyze each individually without it being one completely dissolved sample. Okay, so what is laser ablation, and specifically why do we care? Kind of diving a little bit deeper into that concept, there's some specific advantages that this poses for us. First of all, it's very fast, or can be very fast in comparison, especially if you consider some of the ways that this technique started. It has its origins in geochemistry, where people were using perchloric acid or HF, dangerous acids that you'd prefer not to have around in a lot of cases. You'd have to go through that dissolution step, which can be time consuming. You also end up with waste that if you have the expense of the acids. So this can be very quick. It can reduce that cost and the labor intensive sample prep. I always take pause there to say that I get questions with folks that ask if they're able to just take any sample and place it in a sample chamber and ablate it. And the answer most of the time is, yeah, kinda. Like anything else, I put into the better the end result will be. But at the end of the day, the sample prep is normally quite a bit quicker than it would be through dissolution. Well, all we really need to worry about is making sure that we have a flat surface and that it is perpendicular to the beam coming down. Okay. How we mount it and whatnot, of course, comes into it as well. But like I say, in most cases, the sample prep is minimal in comparison. You can also use this with the technique with just about any kind of sample. I've mentioned a couple of examples with microchips and rocks. In ecology, otolith is a very common application, and otolith being essentially the bone found within a fish's ear, and gives quite a bit of information. Can tell an ecologist anything from the diet of the fish to where it's been in migratory patterns. So lots and lots of sample types. Liquids are also possible to ablate, as are powders. Okay. I've already mentioned the spatial resolution that you're able to maintain with some applications. That's incredibly important. We talked about rocks before, or crystals within them, called zircons, which have growth rings similar to trees. If you want to be able to analyze the chemistry of the various growth rings, being able to do that through dissolution is impossible. If you use laser ablation in very small spot sizes, you can see each growth ring individually. You can see a tremendous amount of information and learn about that rock's magnetic process. You're also able to do depth profiling with the technique, which can also be very useful. With some applications, I used microchips earlier, I'll stick with that. There can be a layer of gold found within microchips that, of course, if you were to do dissolution, would just become a portion of the mixture. But with laser ablation, you're actually able to drill down through the sample. You can find that layer in particular and analyze it, and even any contaminants that might be within the gold itself. So very, very advantageous there. Now, when we talk about laser ablation versus other techniques, it has a lot of advantages. I always say that all the techniques have significant advantages, and they all have a place in your analytical tool belt. But laser has a really nice place where it fits because it doesn't have a lot of the limitations that others do. For instance, glow discharge, GDMS, is a tremendous technique, but there are some challenges with it. Specifically, you're limited in the size and shape of the samples that you're able to ablate. XRF also has some really nice advantages, but you have the obvious limitation of detection limits. With spark emission, non-conducting samples can be a challenge. And laser ablation just gives you a really nice mix of all of those with regard to the sample type, being able to do bulk, spatial, or depth analysis and work with just about any kind of sample. So what does laser ablation look like? Well, this is obviously extremely simplified, but my goal here is to show you on the left side of the screen where it's labeled UV laser. is our laser source or our light engine. It's where the beam originates. You'll see that line coming out of it hits another line there and bounces off to put the light down into the sample chamber. That one bounce is, in this case, indicative of the full light path, which I'll show on the next slide. But the idea essentially is that we take that beam of light, it goes through a number of optics, and then goes down into the sample chamber to strike the sample. You'll notice that the camera itself sits directly above in line with the sample, which is extremely important as it allows us to view the spot without having to have it off axis and view on an angle. Once the sample is ablated, the analytical plume that I referenced before comes up into the cell and is then swept through by the carrier gas and into the torch. As that happens, there's a couple of gases that can be put in, including the argon makeup that you would expect. We also bleed in a small amount of nitrogen, which can help boost sensitivity. All the gases that we're talking about here have their own mass flow controllers and are controlled within the laser itself. So to expand on that light path that I spoke about before, here we show it for an Excimer system. Towards the bottom left, you see that light engine again, where that beam is produced before it passes through a shutter, allowing us to turn it on or off, quite simply. The beam then bounces before going through an optical attenuator, which allows us to reduce the power of the beam, and eventually makes its way to a homogenizer. Homogenization of the beam is extremely important. What it does for us at the end of the day is it makes sure that the entirety of the beam is homogenized. It's all the same. There's no hot spot in the middle. That's what would happen if you weren't homogenizing. Is essentially you'd end up with the middle than it is on the outside. The way that we do that is we actually take the beam, we split it apart into a lot of small beams, and then put it back together. And that works very, very well. The result of that is that you end up with a perfectly cylindrical, flat-bottomed crater, which is extremely important for the technique. If you didn't, because the beam would be hotter in the middle, you'd actually end up with a conical shaped crater instead. And that makes a lot of this quite a bit more challenging. It's important to remember that even though we're ablating the surface and what on a very small scale looks like basically an explosion occurring, it's all very well controlled, and you get a feel for that based upon just how beautiful the crater shapes are, and as I say, how true to being cylindrical and flat bottomed they are. So after the beam leaves the homogenizer, it goes to an aperture where we're able to restrict the beam size and basically cut it down to the spot size that we'd like to ablate on the surface of the sample. We can use a variety of spot sizes. Our Excimer systems, as a for instance, have up to 60 spots that you can use. And we have the option for the use of X, Y, theta options as well, which extends that quite a bit further. So essentially, you have the opportunity to go all the way down sub-micron to as big as 250 microns, depending upon the systems they're using. So quite a big difference. The idea, of course, with smaller spot sizes, you get better resolution, especially with sample mapping. But with the larger spots, you're going to get more material and be able to increase sensitivity. So we always tell people, typically, when we're doing our method development, we like to use the smallest spot size that we're able, where we still receive the sensitivity that we need. Okay? And then you'll see the beam continue on through a number of bounces before it reaches the sample cell and the ablation occurs. We want to keep the number of bounces that occur to a minimum, because every time the beam strikes one, of course, you have a little bit of loss. That's just the sheer physics of it. But we intentionally keep those the number of bounces as small as possible and I believe that we use fewer than anybody else in the market, which is wonderful. You'll notice there's a couple of other things here, including rotating polarizers, which are important for being able to view different samples differently depending upon their makeup, and the lighting used. 3 different lighting sources are also employed here. I include this slide because I like to point out that you can essentially think about the laser, you know, maybe a little bit oversimplified, but you can essentially think of the laser as an auto sampler for the ICP. At the end of the day, what the laser is really doing is it's taking some amount of material and it's delivering it to the ICP-MS itself for detection. So in this case, of course, it tends to be a little bit more expensive than your typical auto sampler, and there's a little bit more to it. But as I say, at the end of the day, that's the main goal. Is it's just getting the material into the ICP-OES or the ICP-MS itself. Now I've pointed toward the sample chamber a couple of times, and I made reference to the fact that we'll do a whole history of sample chambers and the development process in subsequent seminars. For this one in particular, I'm simply going to show you what our primary sample chamber looks like on our Excimer systems. We call it the HelEx 2 sample chamber. It was developed in Dr. Reagan's lab at ANU in Australia. This is the second iteration of it. It is the most peer-reviewed sample chamber in the market today. We're extremely proud of that. And it allows you to place your samples in a variety of ways. You'll notice the brass chamber over there on the left has an arm that sticks into it and a metal drawer that sits underneath that arm. It's within that drawer that the samples are actually placed, either through 1-inch round pucks, where you would take a sample and place it in an epoxy before analyzing. It also has 1/2-inch rounds, which are often used for standards, and it has a place for 4 thin section or petrographic slides, more often than not used for biological samples and the like. Now that cup always sits in exactly the same place, such that the laser beam comes down through the top of it, goes down through a small hole in the bottom and ablates the surface of the sample. The sample chamber and the samples that are within it, of course, move on stages such that we position the sample underneath that cup. Then when we pass the beam down through it, it strikes the sample, the analytical plume comes up and is kind of pushed up by a flow within this outer sample chamber that meets a flow that's pushing down from the top of the cup. That's what's illustrated on this picture on the right, is these 2 flows kind of coming together to push that plume into the sample arm, which leads directly to the ICP-MS torch. What that process, the amount of time that it takes for all of that to happen is referred to as washout, and is an important term that you'll often hear when people are talking about laser ablation. About 5 years ago, having a washout time of under a second was considered very, very good. That's changed since that time. The sample chamber that you see here now, the HelEx sample chamber, has a standard washout time of between 600 and 700 milliseconds. So 600 to 700 milliseconds, also very strong. We released a product a couple of years ago that I know many of you are already familiar with, called the Iris, that we'll talk about in the subsequent presentations. For this purpose, right now, I just want to point out that it essentially allows us to take the effluent and place it very, very quickly into the torch. We're able to take that washout time from about 600 milliseconds down to about 30. So a tremendous improvement there. Okay. Now, talking again about the laser and the wavelengths, we have a variety of systems that we make, ranging from fusions systems, which are intended to heat samples, all the way to femtosecond systems, where that's exactly the opposite of what we want, and everything in between. The way that we do that depends upon the laser itself. For our 213 nanometer system, we call the LSX 213. It's a neodymium YAG laser. The way that that works is it starts as a 1064 nanometer beam, and then that beam passes through a series of harmonic crystals. And depending upon which crystals are used in what order, we're able to change the wavelength of that beam. And you'll see by using a second, third, and fifth harmonic crystal, we're able to change that 1064 down to the 213 that we offer commercially. When I first started in laser ablation, my product manager at the time explained that process to me and just referred to them as the magic crystals, and said, well, there was a tremendous amount of detail in physics that could be shared. That conceptually worked pretty well, and that's all you really need to know about. I always found that a very humorous anecdote. Now, you'll notice that there's also 193 nanometer lasers that represents the vast majority of what we sell today. That starts as a 193. There's no magic crystal necessary there. And we do also offer femtosecond systems, each having their own advantages and what they offer. Showing that a little bit, talking about the wavelength and coupling efficiency. The idea typically is that as you analyze materials that are more clear or translucent, transparent or translucent, you want to use a shorter wavelength because they couple better to it. Okay? What I mean by that is that if you were analyzing quartz, as a, for instance, a clear material like that, you would want to do it with a 193, the narrowest of those wavelengths, because it couples well to that material and you end up with a better ablation because of it. Now, if you were to use a 213 as an example, where you'll notice here your transmission percentage for that is about 60%, so you're looking at 40% absorption. That beam tends to go deeper into the material and kind of builds up until you get essentially a catastrophic ablation. That's still on a very small scale, mind you, but that explosion that occurs ends up robbing us of the cylindrical crater that we mentioned before as being our end goal. So in order to have the best controlled ablation, we want to have that narrower wavelength. Now, if you are using opaque material, you're doing bulk analysis or something of the like, then a 213 or even a 266 can work very well. But as I say, as you get towards those clearer materials, or if you're doing biologicals, you'll end up with better results with a narrower wavelength. The next concept I wanted to introduce is fractionation. So in its simplest form, we define fractionation as when the elemental composition of the material being measured at the detector is not representative of the sample's true composition, meaning essentially our result doesn't match what it should have. And there's a number of ways that this can occur. Fractionation increases if you have larger particle sizes. If your particle size if your particle sizes vary, you have some big, some small. That's what we mean by PS distribution, particle size distribution. And if they differ in mass or volatility. So in an ideal world, perfect sample type, we would want very small sizes. We'd want them to be consistently small and have a similar mass and volatility. By doing that, you get the most representative sample result. Okay. And kind of giving you a visual, a little bit of this, and something they can contribute to it. I want to talk about the difference in the way that the sample looks when it reaches the torch. Most of us are familiar with or spent the majority of our career doing liquid nebulization, where you end up with this very consistent, flat, high sensitivity signal. Laser ablation is different because you're actually taking particles and putting them into the torch. So it tends to be less consistent. You can have large particles that aren't ionized at all. So you can actually see them here entering the torch. You'll also notice that if you're looking at the corresponding MS data, that the signal would appear much noisier than it would with aqueous analysis. But in this case, all of that, quote unquote noise is all very real data. It's just all coming from the individual particles as they're being ablated. So it's just a little bit of a different way of looking at it is all. Okay. Now, kind of furthering that, this graphic is intended to show exactly how that fractionation can occur and what I mean by the distribution within. So if you look at this large particle here on the left, we show it as kind of being split in a number of ways. Our goal is that we would like the elemental composition to be well distributed throughout, so you don't end up with trapped particles, which can lead to a poor representation. If we have the smallest particles possible, then that becomes much harder to do, and you end up with a more representative sample. Okay. And then just as one final piece on this, I think this slide does a really nice job of pointing out the different wavelengths and the advantages or challenges with any of them. You'll notice as you go lower and lower with the wavelength, your heating effects fall off, which of course is our goal, unless we're, as I said, using a 1064 for the intent of heating. We also end up with far less fractionation when we're using a 193 or femtosecond laser and a narrow particle size distribution. So I always tell people that a 193 can do everything a 213 can do. It just typically does it better. Of course, there's some other challenges that there are different price points and complexities and all that sort of thing. But you can obviously see why the market has trended towards 193s as the technique has become more mature and less and less pricey. So for those of you that have not seen laser ablation in the past, I thought it was important to show exactly what this looked like. So this is a sample actually being ablated, a simple raster on the surface of a metal sample. So you'll see the serpentine pattern. Just a very small amount is being taken off the surface at any given time and put right into the ICP. And then I've already touched on what can be ablated. Well, this varies pretty significantly because just about any kind of sample works. Zircons are certainly a very, very common sample to be ablated because we work with a lot of geochemistry laboratories. They are the crystals that have the growth rings that I mentioned before, for those of you that are unfamiliar. We also work with people doing ice cores for climatology and paleoclimatology. As you would imagine, we have ways to cool our samples even within the sample chamber, which is nice. And then you'll see a whole host of other variety of samples, including paper for forensics, hair. Biologicals are becoming far more common. And especially when talking about sample mapping, which we'll touch on shortly. And then to give you an idea of what these systems look like themselves, our 213 system that I've referenced before is the one on the top left, with our Excimer system, Excimer systems being down below it, and our femtosecond system being in the top right-hand corner. What I'd really like to point out is that the sample chamber that you see and the 213 system and the Pharos, it's the same sample chamber. So it gives you kind of a nice view of the scale that we're talking about here. That 213 system fits nicely on a bench top where the Excimers are floor mounted. Kind of provide their own table, if you will. And then the one system that I didn't have on that last slide is our newest offering called the Iridia. It will be a big portion of next week's talk that Damon will provide. The Iridia is a tremendous system. What's going to sound a lot like sales rhetoric and hyperbole, if you'll forgive me. The Iridia is a culmination of a significant evolution in laser design, specifically because it's so fast. It has laser speeds of up to 1,000 hertz. It also has washout times that we talked about before. We talked about having 30 milliseconds be exceptional. This system is actually capable sub-millisecond washout times. So the resolutions that come from it are pretty incredible. And then where I want to finish up is talking a little bit about applications. You know, we've already talked about that can be used. I think this does a nice way of putting them into the markets in which they apply. Earth sciences, as I mentioned, is a really big one for us. I spend a lot of time in geology labs or geochemistry labs. Forensics is another. We showed that ink on paper before, which is very neat. We've also seen analyses that have come from broken glass. Maybe there was a burglar or something that had a piece of glass that was left in their clothing. They were able to analyze that glass and match it back to a burgled home or business. Same can be done for paint in the event of a hit and run or something, where not only the paint can be matched, it can often be matched to within a specific lot. So very, very neat stuff. Archaeology is a great one, whether we're talking about pottery shards or bone. There's some really neat applications out there. So to show you some neat examples, this one I think is neat for a couple of reasons that I'll get into. What you're looking at here are stalagmites that were analyzed from a cave that was near an old Roman gold mine. And when you actually analyze these samples, we, and I'm using the word we very loosely in this case, someone other than I, was able to look at the specific growth band within the stalagmite caused by the drop in the cave, and be able to find the exact timeline in which that Roman mine existed. And you can actually see the gold layer that appears there in the middle. So very, very neat. The other reason why I like this slide and to talk about it is that with stalagmites, as you can imagine, they're growing as the water drops onto it, right? And so as it grows, it's not growing. It's not growing in a perfect layer. The growth pattern is not parallel to the cave floor, if you will. Instead, it creates kind of an arc. So what's nice about laser ablation is that you're able to look at a slice and be able to follow or trace the actual line and take a growth, an entire growth ring, as opposed to just taking a slice, which may incorporate several rings. Okay. I've mentioned zircons a number of times. Zircon analysis is as I say, kind of our bread and butter. We do an awful lot of work in this world. It used to be done almost exclusively through the spot analysis, where a researcher would identify a spot within, and they would blast a hole in the middle of it and look at the resulting chemistry. What we've seen more and more and more of now, because of the smaller spots that are capable and the speeds that are achievable, is that people are looking at mapping the entirety of the crystal. You'll see here, this crystal can be mapped in less than 10 minutes, and the amount of information that can be gained is pretty profound in comparison to a single spot. Especially with the smaller spot size that are being used, oftentimes we're able to see growth rings that may have otherwise been missed. And this is one of my favorite slides. What you're looking at here is a garnet that was analyzed. It's a fairly big garnet, greater than 5 millimeters in size. And this was analyzed in only 48 minutes, which is, again, a pretty tremendous advantage. If you were to think about this being done by microprobe, as for instance, it might have taken over 14 hours. You'll see it cycling through the different elements, so it's important to remember that each pixel contains all of the underlying elemental information, and yeah, it's very, very cool to me. Okay. The last example that I want to show then is of a stain that was then analyzed, and with the elemental data overlay. One of our softwares that we utilize called HDIP allows for the import of imagery from different sources. So you can import SEM data or X-ray data if you'd like. Stains like this could be imported. So what you end up with then is if you were to overlay, excuse me, the data on top of the slide, you can end up with a beautiful example like this, where you're able to see intensity in the Z. And this can actually, this is a video that can be created within the software HDIP in order to give you a flyover, be able to look at the individual features. Okay. Now, also utilizing HDIP, which I mentioned before is a secondary software that we utilize for data interpretation. We're able to look at a lot of mapping and samples and control the imagery that's created. It has a tremendous number of options available to you as a researcher, including the ability to look for regions of interest, which are identified automatically. It's extremely automated to assist you in your efforts, and is wizard-based as well. That's one of these things that we'll talk about in a lot of detail in the upcoming webinars. What you're looking at here are the different villi in the small intestine of a mouse. You'll see that the imagery is excellent. Down there at the bottom, that is a scale of just the zinc being shown with the full mapping there. In this case, we're using 1 micron spot sizes, so very, very small, excellent resolution, and the total acquisition time in the sample was only 35 minutes. Okay. We're also able to generate 3-dimensional images on a very large scale. So we talked about zircons before, and typically the analysis of the zircon is done 2-dimensionally. What we've done here is we actually utilized a microtome to go through and do the slicing of the sample very thin, and then analyzed each slice in a total of 100 layers before the HDIP software put all of those layers back together and generated the 3D image that you're seeing there. Okay. That can also be applied to biologicals, where in this example, you're seeing the analysis of a water flea. Okay. It's a little hard on the water flea, mind you, but with that being said, you're able to again see the individual layers that were stitched together to create the 3D rendering, rotatable 3D rendering that you're seeing there. Pretty incredible stuff. And this is all again generated through HDIP, which does a really nice job of providing you with options as it relates to the imagery and data processing. Okay. So I'm a little bit over on time. The last slide that I have for you is simply to tell you a little bit about the upcoming seminars. So as I said, this was really intended to try and fit several hours worth of information into a 30-minute discussion. We were close. We did it about 35. But we're going to get a lot more in depth in the next 2 weeks. Specifically, Dr. Damon Green, who is our product manager as well as our vice president of market and technology, is going to speak next week. Damon is a geochemist and is going to go through the evolution of LA-ICP-MS through collaborative science, basically showing the development of new sample cell designs, not just how the sample chambers and the light engines have evolved, but how they've got us to where we are and where the technique is going in the future. Beyond that, the week following, Ciprian Strepton, who is a brilliant geochemist as well, is going to speak on applications of laser ablation in a lot more depth than I did today, showing a lot of examples and utilizing HDIP to show you exactly how we can interpret that and get the most out of it. Okay. everyone should receive or should probably has already received a couple of emails with invitations to those. I'd greatly encourage you to sign up. Okay.